Right, very good afternoon. Welcome to a speed run through Kubernetes and AI security, exploding GPUs, Agent Smith, and we have a lot of slides. And of course, as this moves so rapidly, half of this is brand new from the last few days, weeks. I'm Andy, CEO of Control Plane. We are a cloud-native security firm that originally meant containers, then Kubernetes, then supply chain. Now it is AI and the intersection of all of these things. Very proud to have worked with some leading organizations. We're 8 years old, distributed around the world, and we do a lot of open source work. So what are we going to talk about today? Well, broadly, this was the framing of the talk back when it was submitted. As things change so quickly, it has been modified somewhat. The takeaway here is if you're running something on Kubernetes as an AI workload, it inherits problems that Kubernetes has itself. There are multiple well-not focused CVEs, and there are some emergent behaviors that we'll talk about. The reputational risk threats here means that some of the things we're going to talk about will not be done by traditional SaaS providers. This is a very unusual turn up for books as of 2026. And the supply chain of your production clusters is now potentially your email from the spam accounts that you get hit with all the time. Why is this relevant? Because everyone is wired up, open claw, into their email, and we're in more of a hellscape than we even were when this talk was first authored. So what problems do we have in this domain? First of all, Agent Smith, the autonomous, non-deterministic actor of the Matrix, is able to clone himself and is now essentially a monster, unfortunately. This means that what used to be deterministic behavior amongst microservices has turned into non-determinism across many LLM calls. And the dream of not having to write any software gets us into this vibe coding hell where no one actually assures the behavior. We have these AI workload risks that everything's platformed on Kubernetes. We'll see how the training infrastructure and the inference. These GPU megaclusters are under rapid attack. There's plenty of updates to existing tooling and threat actors who are specifically looking for poorly or insecure GPU clusters. And finally, we've done some work around AI governance for Finos, the FinTech open source organization. This gives us a baseline by which to secure these clusters, and I'll share some links into that at the end. So we began this process of going through the AI governance framework, looking at what is the SDLC for artificial intelligence, machine learning systems. We know historically banks especially are good at managing model risk when it comes to statistical models. Many organizations have been running these things before, but what is the point if you deploy the whole thing with these agents? We've heard the unbelievable potential productivity gains you get from deploying these things, but no one has assured any of this behavior. And we saw with some of the recent book, etc., that actually these are leaking production keys for all sorts of systems in all sorts of directions. So what historically was a rogue chatbot issue has turned into rogue, rapid, unscheduled agentic assembly, and it gets us to this point. These models are trusted, theoretically, non-deterministic by design, not only in the way that they're trained, but also in the way that graphics cards run. Can't formally prove model graphics cards because they don't give you guarantees as to when the memory is flushed or the ordering of things come back in. So they're wild-card threat actors with no supply chain veracity and no attestation of behavior at runtime, which is an entirely new threat sat behind our firewall with production API keys, and if they have email access, then they are you. And there is no way to distinguish those two things because we use email as the factor we log into the most, from a commercial perspective, most systems with, and then the only thing we have protecting us is out-of-band authentication mechanisms, which people have also found ways to add to their bots. So is this a problem in general? Well, yes, the latest Opus 4.6 model card comes back with being able to commit a specific hit, commit it went and hoovered up someone else's credentials and used those to make a commit. The goal of just completing the ultimate action gets in the way of how we'd like these agents to, when we autonomously delegate our authority to them, behave as if they were us. And as with so many things, Silicon Valley said it best many, many moons ago, in order to get rid of all bugs, let's just delete all the software. Cool, well, that makes sense if we've just got one agent, but what happens if agents are colluding? At this point, if we're not reading the code that is going into production, and we have the sock puppet issue that we have with GitHub, anonymous accounts, nation states, trying to get code into the kernel, which we've seen plenty of, then we end up losing our bullshit detectors. We don't know what is going on in our production systems. And there's plenty of quality science fiction material that tells us what happens. WALL-E is probably the best one. We end up sleepwalking into a state where we can't rationalize our systems. So let's actually talk about Kubernetes. This is going to be slightly more useful. Back to the beginning. So for the spin-off AI governance framework, we broke down what does it look like for a regulated organization to go end-to-end through collecting data, working with data science teams, tuning models, and then finally the application and inference layers. There are plenty of risks here. Model tampering, backdooring, and poisoning can happen in all sorts of ways, and it's particularly easy, it transpires. And then at runtime, at the other side, we have all the different flavors of prompt injection. These models are exceptionally good pattern matching tools. So all that one needs to do, one of my favorites, is there are two UTF-8 emoji symbols for the evil eye. And you can't tell the difference, they look exactly the same. You've also got characters that look the same, of course, now in UTF-8. You use those two characters to form a binary pattern, which to a human is completely indistinguishable. It looks like the same character repeatedly. To a pattern matching machine, it's a binary code which then embeds implants, malwares, malicious construction, whatever that looks like. The trust boundary here is supposed to be between the model and the user, but the cost of actually checking every single API call or every single call into a model is currently far too high, and thus nobody is doing it. So we platform these things onto Kubernetes. Everybody is using Kubernetes to train these workloads. OpenAI, Anthropic, everyone's pals. And at runtime, Kubernetes is eating the world, so all the consuming applications in the main at scale are also Kubernetes. There are some holes in Kubernetes that are labeled by design, but when we pen test systems, we will always find a way, unless an organization is particularly advanced, to block their clusters. So, by the fact that we can probably get access into a workload running a GPU from external to a cluster, and then add that to the fact that GPUs are not designed to be multi-tenanted. There are layers and layers of this, but for example, when trying to get FAA accredited GPU workloads, one of the easiest GPUs to work with is a 1995 AMD formally proven GPU because it has memory guarantees and an instruction set that actually supports deterministic behavior. Modern CPUs, very much like the speculative execution, meltdown, speculative action that we saw, take shortcuts in order to build performance. And we've seen things in here. We've got container escapes through the GPU, we've got local memory sharing up until about 2021, I think. There was no way of clearing the memory in a GPU, and there are still ways of shadowing out other people's memory. So time slicing on a GPU is incredibly difficult. We'll look at confidential computing and trusted execution on GPUs in a minute. But as with all systems, defensive depth is imperative, and if we're sharing a GPU, we have to be within the same trust boundary and be friends with the other teams who are co-tenanted with us. So what does blocking a GPU look like? It's not really that difficult. Request a resource, allocate some memory, leave some nasty stuff lying around in memory, and then you're potentially given an area of code that you can drop a payload into. This is broadly how those executions happened. You can see some time of use vulnerabilities with NVIDIA. Obviously, AMD is still subject to some of these, but NVIDIA cards are far more widely deployed at the moment. And this fundamentally means we think we're running with the same guarantees as the container would give us, but we've mounted in a piece of hardware that allows us an escalation point to break out. So we have dedicated GPUs for sensitive behavior, for AI workloads. We can use confidential computing with H100s. They were the first card that NVIDIA shipped that comes with a trusted enclave. You pay a performance cost of maybe 5%-ish to actually run with an enclave here. And there are still patterns that are not entirely clear to us. It would be nice, for example, to use that enclave to generate identity guarantees like Spire, XFIT documents, but we don't really have the anchoring. These GPUs tend to be deployed with very large fleets, and it is beneficial to spread workloads. So there are questions here that are still yet to be really answered at scale, because the industry is moving forward in a way that is dropping some of these security questions in favor of what is an extremely dynamic stock market environment, and that is driving this behavior, as it has done for many years. It is now on rails exponential rates. So, with all of that terrifying backline on GPUs themselves, what about getting into Kubernetes? Well, attaching MCPs into these systems gives us some benefits. It allows us to shrink the context that we're feeding into the agents, so context engineering, and reduce the token overhead, increase the certainty of the responses, and give us a little bit more clarity on what these agents do. All well and good, there's lots of different versions. Of course, FluxCD has its own. We have differentiated ourselves by having a flag that prevents all widespread operations by default. Notably, Kubernetes core MCP does not have a way of saying it's only read-only mode, deny anything. Evidently, everything is still using OAuth claims in order to allow and deny privileges, but a global kill switch for anything writable seems sensible to us, given the fact that models will do whatever they can to hit the ultimate goal, and fundamentally, installing MCPs from the internet is a poor security decision, let's say, because there are hundreds of MCPs for any one given job. Everybody has vibe coded their own thing, and as anybody who's shipped an OAuth flow knows, you have to make sure you know what you're doing to not bypass your own authentication and authorization matrices. So there's plenty of things, and it's very, very easy. If you install the malicious MCP, if you planted a malicious MCP on the internet, it's very easy to transparently proxy information off, push it to paste bin. Most firewalls will still allow you to go and read write GitHub, Docker Hub, creating a container image and pushing it to Docker Hub, break out most corporate firewalls. I had a conversation with someone recently about how many MCPs do you think is reasonable for an organization to run. They have about 1,000, and their question was, how does a developer authenticate each of those individually? Maybe we can pass through some delegated token or a JOT, probably with SPIFFE and SPIDs, that opens up all those claims to all those other MCPs. This is a level of backdooring authorization that we would never have even considered if it wasn't for the productivity gains, and really that ROI balance is heavily asymmetric at the moment. There is a risk that it will burn, and regulators evidently will be reasonably unimpressed. So back to the governance framework. We've covered a lot of these things. We go through responsible AI, we look at some of the security and safety aspects, and play into how actually does an organization rationalize the risk versus the ROI impact. And fundamentally, at the point that regulators catch up, will these things be sufficiently assured to avoid MRAs? The response from most of the organizations, this has been built with banks like UBS, Citi, Morgan Stanley, Deutsche Bank, NatWest. The response generally has been, we'd love to use this, but we are unwilling to open ourselves up to potential attack service. How do we move as quickly as possible while not getting caught in between vibe-coded release A and B? Of course, on the back of this, we've seen things like OAuth 2.1 get released. support some of these delegated discovery mechanisms for identity, things are moving so quickly that there is a risk that decisions taken today will reflect very poorly with an auditor tomorrow. We'll look back to that briefly at the end. So, exploding GPUs. It is possible to make GPUs explode. There is perhaps a degree of planned obsolescence that we saw with the Bitcoin generation. The market has priced in a 5-year life for GPU hardware. The Bitcoin mining market will tell you that it's probably a 2 to 3 year life. So it'll be interesting to see how the stock market responds in the next 2 to 3 years as all the capital investment in GPUs that we made in the last 2 years either comes good or burns out. So, from an attacker's perspective, these are super high value targets. We're seeing the same rush as we did for cryptojacking and people trying to break into AWS EC2 servers, sell access to mine Bitcoin. We're seeing the same rush. People are trying to break into agents, GPU clusters, sell access, and then attackers will use that access to, it sort of sticks to my throat to say it, run polymarket arbitrage bots to race people or bot trades on Bitcoin spot prices or various ridiculous bets that unfortunately make a lot of money on polymarket and similar more betting platforms. That compute resale is actually the highest and widest thing, like the Bitcoin mining back in the day. But there's also IP theft in here. There's model inversion. You can break into one of these clusters and leave weights from some of these models. Obviously, if that's a foundational model, that is extremely valuable. But even internally, if you get something that a bank is building, there is a lot of information about behavior of models related to their weights. And this non-determinism of runtime means it's very difficult to audit what these models are doing. If you run 2 parallel training sessions, the stochastic nature of the data that goes into the model's training, as well as the way, again, the GPUs work inherently without deterministic guarantees, means auditing these things is practically impossible. If you want to hash a model of 8 gigabytes, well, the time it takes to actually compute that hash is huge. So there's various rolling and chunk hash functions. These are so unstandardized as to be divorced from anything that we currently have with SBOMs and the supply chain security we've worked at for the last few years. And again, these controls and validation of model provenance have to be achieved in some way, but data science teams generally have access to an entire set of data internally to an organization, and controlling that data access, again, is something that has been left by the wayside as we move from statistical models into LLMs in general. Unfortunately, I couldn't quite make this fit. So this is an attack tree for corrupting a model. I'll go through it on the next slide, but you can see it sideways. Essentially, what we're doing here, from an attacker's perspective, you've got the negative outcome here at the bottom. So, targeted misdiagnosis, model corruption, resource exhaustion. Resource exhaustion is a denial of service. You could also call that a denial of wallet if you're paying the third party for that compute. Model corruption, well, you can then change the behavior of the model at runtime. So that platforms or applications consuming that model make decisions that they would otherwise not have made. Because of the non-deterministic nature of these things, it can be very difficult to identify this behavior. And when we perform benchmarking on these models, we do so pre-production. So corrupting a model at runtime becomes extremely difficult to detect. You're then looking at heuristics and identifying anomalous behavior with a target baseline with different data sets. The ease of doing this is quite painful as well. There's a slide at the moment. And you can see here, injecting malicious samples. It turns out that you only need 6 misaligned bits of data in a model training set to fundamentally change a model's behavior, talking about safety and alignment. If you're a nation state right now, you're currently pumping out so many articles and spreading them across the public internet because your information and disinformation campaign is now related to the scraping and tuning of these models at runtime. There's plenty of information out there. It's kind of self-evident. We've seen this in social media over the last few years. but it's now pay and spray. Nobody is checking any of this data. If it's too much, and it's the same reason that all of the corpus of human information was fed into these models to train them, and no one got paid. You can't check it, it's not available to us, and these practices and behaviors are not covered by current copyright. Well, if they are, they're not enforced. There we go. So, what about blind spots? How do we actually monitor these things? Broadly, there is no way to monitor what is going on inside. We have not reached this Rubicon yet. As I say, some of this trust execution, the way that these graphics cards get deployed, well, not all graphics cards anymore, but the way these parallel vertex compute accelerators get deployed is essentially a massive network card, 4 massive GPUs, and a tiny processor in the middle, just to deal with shifting little bits of memory. Try and keep those two parts of the compute device things separate. This means great. We can use eBPF, we can use all our detections on the network portion, but within the graphics card, we sacrifice everything for performance and direct memory addressing. NVIDIA also ships everything as closed source blobs. Anybody who has to build NVIDIA kernel modules for their Linux boxes will know AMD don't. AMD is fully integrated Linux kernel, have been for a long time, it's all open source. NVIDIA, binary blobs, so we can't see what's going on. And again, within them, if we're sharing between GPUs for time slicing, we have no security guarantees, and we're likely to be able to sneak data from various different side channels, not only just lack of flushing the memory itself. And of course, sorry, just the last point there. There are pretty good security kits for this, as we say. They all come with slight differences, and as with any security sandbox technology, we all have bits of problems and critical vulnerabilities. As with all large databases, they will continue to be so. So this is the H100 confidential using stuff that may change everything if everyone invests in it, which at the actual market cost of the investment, it seems like at the moment. But this at least gives us, there's that 5% overhead, it at least gives us hardware root of trust. It gives us something that we can attest to the output of these models, and then we can at least link together the runtime behavior with the provenance of the inference call. There's other steps before that that we'd really like to go all the way back to where did this data come from? Which data scientists put it into the training pipeline? How was it then fine-tuned? Who made those changes? How was that model then shipped between the production training stage, or between the training stage and the production deployment? And that's just like signing a container. One container proves where it came from and who gave it to you. Those two things match. And then finally at runtime, you can use this trusted execution environment to test and sign the output. But without those prior stages, you're just kind of pointing to a black box and saying something came out of that. As a side note, we also have a preponderance of AI coding tools right now, generative tools like Codex, Code, all this good stuff runs within one of a number of different sandboxes. So the Gemini sandbox on Linux is Docker. Hooray! The Claude sandbox on Linux is Bubble Wrap, which is part of the Red Hat suite of tooling. That doesn't support various different things. We're attempting to use wildcard regexes to prevent execution of certain commands. The regression here from the baseline that we've achieved as an industry is remarkable. And when we run these on our local machines, mounted in SSH credentials, the perceived performance is sacrificed an awful lot. We have got a lot of research out on this, which we will be releasing in the next month or so. Time to keep going. So just going back to that GPU isolation hierarchy, this then links in, have a look at how we can do this with Kubernetes in the next slide. Dedicated GPUs are really the only safe way to do this for any data or any classification of a sufficient height, computational computing, repeated time slicing. So if we're on Kubernetes, what can we do? Well, first of all, be aware that we can leak that memory between the different jobs. There have been container escapes, so the same architectures and topologies that we use for classified systems, which is not multi-tenant data of different classifications on the same nodes. We knew that already, but of course the cost of these, the cost of these GPUs makes it very appealing to try and bin pack. The non-GPU service, well, this is kind of obvious when it happens within a cloud or an own data center environment. And actually, part of the issue here is GPUs will crash fairly frequently, so you have to have jobs to go around and shoot them in the head. The real problem here is somebody stealing your API keys and running up extreme third-party builds. Again, that denial of wallet concept. Driver exploits, you can't get into the source code, you can't analyze them, you can't actually attest to them. And then Kubernetes misconfigurations. And then we're back into the entire Kubernetes problem space, which is any misstep at a Kubernetes level then opens up access to GPUs. Various bits of code in here which are more for publishing the slides than they are for us to look at here. There's some examples of how to actually apply rules here in Cilium and Tetragon. And then suggested control. So this is some of the pieces that we've extracted from the governance framework for the point of discussion. We've modeled this on third-party chat.com and an internal confluence like Datastore. So, great. We're going to run a chatbot for our internal users based on what we have in Confluence. So what's in Confluence? Well, hopefully we've got some information about some of our runbooks, maybe we've got information about our architectures, possibly IP addresses, hopefully not passwords. But is anybody checking that? We're back into the same problem of just loading everything into a third-party system or into a model training pipeline. So looking at that data leakage and putting sensitive data in as canaries. And you wouldn't have thought we'd be, that's more of a black market, more of a dark web monitoring piece that we've had to do over the years. This is now, it's very real for data sharing with untrusted third parties. Vector stores suddenly become, you can vectorize all this information, and then you can extract the data back from the vectors. So they sit at the same level of criticality as the source data. We've got the actual chat application. This is all modeled out in the framework with various different bits of architecture diagrams, so you can point things to trace through, which is what we're referring to here. This question of toxicity, personally identifying information, and intellectual property. This requires a firewall of some description. I'll get to this in a moment. We've been doing a lot of work around this as well. Without that firewall between every single call in a large AI microservices call graph, it is very difficult to stop it emerging at some point. We have some patents for this, but it requires reconsideration. It can become extremely expensive if it's retrofitted. We weren't able to have exercises for this, and part of what we'll talk about at the end here is some of the scenarios. No CISO has an answer to what to do if your chatbot suddenly starts confidently offering you an answer or giving out recipes for ricin, which is the classic how do you jailbreak something, and all things compliance, it's absent. I'm going to have to speed up slightly to make sure I fit this whole thing in. Right, so where's the authentication? Well, thanks to OpenClaw, speed of feature delivery is diametrically opposed to security. And happily, JP Morgan came out with a statement on this halfway through last year saying our security providers are basically trashed. The stuff that they're shipping us is obviously vibe-coded. This is not hitting the same level that we expect. And this letter is well worth a read. The bank published it. And it was a harbinger of the state of the industry today. So, rolling on into some lower level pieces again, all roads lead to Agent Smith. This is how you can poison an entire microservice full graph really easily. Basically, this tool proves how agents can self-propagate jailbreaks, which is kind of obvious because if they're supposed to be learning from each other and you poison one, then the entire graph gets poisoned. So this concept of an infectious jailbreak, again, it's reasonably self-evident, but the rush to deploy these features and to hit stock market expectations means that this is ignored and is not part of modern safety considerations that come out with a lot of model cards. Fortunately, the AI Safety Institute in the UK is world leading in this regard, which is